Okay, thank you everybody for coming in. Today it's a great pleasure to have Lev Beklemishev in. He will give a talk related to Gödel incompleteness. And Lev did his PhD in 92. He did his habilitation in 98, all in Moscow. Then he was for 1 year in Germany with Alexander von Humboldt grant. He was 1 year afterwards in Austria with the Liesel Meitner Fellowship. And he spent 5 years in Utrecht. Then he went back to Moscow to become full professor over there. He had a high function in Moscow. He was deputy chair for 5 years, from 2017 to 2022. And currently he is head of the logic group in Moscow. Moreover, we have very famous guests. Harvey Friedman is in as participating via Zoom, and Balthasar Grabmeier, and I don't know who else, maybe some more, let's see. Yeah, Luke Dowling, Swapnil Ghosh, Yet Vanave. Yeah, so, okay, so please.
Yeah, thank you very much. So this talk was announced a little bit on the short notice, and my understanding was that this will be a kind of less formal talk where everyone is taking lunch, but it turns out to be somewhat more formal after such an introduction. But anyway, so of course, Gödel incompleteness theorems are the most famous results in logic and also maybe mathematical results outside mathematics. It's a big task to survey everything related to Gödel incompleteness, which I will not plan to do today. So my purpose today is to present 3 examples, or 2 or 3 concrete examples of formal systems that are sort of violating the sufficient conditions of Gödel's second incompleteness theorem. And they demonstrate in this way the boundaries to this Gödelian phenomenon that we have. And of course, the history even of that, the study of boundary conditions is a deep one. So in the 50s and 60s, it started perhaps with Kreisel and with Pfefferman, who, Pfefferman's thesis was called arithmetization of metamathematics in a general setting, where the purpose was, well, the task given to him by Tarski was to present a more general version of Gödel's theorem, not on the level as Gödel himself did. So Gödel provided one concrete example of a formal system and then said something like, of course, the same ideas will work for almost any other formal system. But this was somehow stated less formally, but in Pfefferman, where he tried to obtain more general formulations, and then he again discovered that there are certain obvious obstacles on generalizing this. And the first obstacle is that, firstly, the informal statement of Gödel's second incompleteness theorem is like that. So under certain conditions, formal theories cannot prove their own consistency. Now, spelling out these conditions is a separate matter, but what Pfefferman paid attention to, and following Kreisel, that this, in order to state Gödel's theorem, theories need to be able to state formally what a consistency assertion is. And there are problems with this because our metamathematical informal understanding of consistency does not directly relate to our formulas that we write in our formal system. So the main, let's say, philosophical problem with G2 is that the meaning of consistency, of what it means for a formula to express consistency, is not well spelled out. There are certain approaches to explaining it, and I knew some logicians of old generation, like Vladimir Uspensky in Moscow, who actually did not really believe in G2. So he considered G2 to be a somewhat imprecise statement, unlike the first incompleteness theorem, which is well understood from the point of view of, let's say, recursion theory or computability. So anyway, so the meaning of, so what it means that a formula or a formal expression expresses consistency. So that's the first counterexamples, the simplest one, coming perhaps from Kreisel, were the following. So the standard, let's say, model theoretic approach to the question of definability, or what it means to express, refers to models. And usually one says, okay, the formula expresses a certain predicate of natural numbers if it is true, if and only if on those numbers for which this predicate holds, like, formula x plus x equals y. Okay, expresses that the number y is even, because in the standard model it holds only for even numbers. Now, something like that clearly does not work in the case of expressing consistency. Simply, well, one reason is that consistency assertion is just a single sentence without free variables. So in the standard model of arithmetic, it is either true or false. And a priori, it's not even clear what's the difference between any particular formula and the formula, or true formula, and the formula 0 equals 0. So that's a problem here. So coming to this Kreiserian example, so that if one, for example, defines, so it is known that Gödel showed how to define in arithmetic, let's say for piano arithmetic, the so-called proof predicates, and using the Gödel numbering. So it's an arithmetical formula in two variables, x and y, which is true if and only if y is the Gödel number codes of a proof, a proof of a formula with the Gödel number x. So one can do that somehow, as Gödel showed, in one way or another. Well, then from this formula, one can redefine the notion of proof and say that Rother probability. So we say that formula is provable if it has a proof, such a proof, but it is provable in Rother sense. So let's say Rother probability if okay, y is a proof, and for all z smaller than y, z is not a proof. So if x is now the Gödel number of a formula expressing contradiction like 0 equals 1, then this will be, well, again, a formula in variable y, which is true if and only if why is a proof of contradiction? Well, however, one can show that in fact Rosser's consistency, so consistency of PA in the sense of Rosser probability will be provable in PA, right? So we have something like con R PA, where con R of PA is the formula that's for every y, the provable 0, 1, y, something like that. So in the sense of, well, assuming PA is consistent in the standard model, this formula expresses the usual probability predicate. However, if consistency is stated in terms of this formula rather than this formula, then the opposite of Gödel's theorem holds. Well, that example, of course, can be rebutted and was rebutted by simply saying that, okay, this is not a natural expression of probability, right? So that's, in fact, if we read this formula, let's say, not interpreting it in the standard model, but just reading what it means by reading the content of this formula, then it expresses a certain different property. Not the fact that just y is a proof, but in fact something in addition comes here, some additional condition. And so one can just say that Rosser proof probability, it does not express, or as one said, naturally expressed probability in arithmetic. So therefore, this example is a sort of a non-example. Okay, Pepperman produced even more impressive counterexamples of that sort, and they influenced the discussion around Gödel incompleteness theorems for a long time. So, in fact, yes. So the results of Pepperman can be summarized as follows. So he first formulated certain syntactic conditions on the formula, on this formula PRF, that would be sufficient to obtain second incompleteness theorem in Gödel's form. And secondly, he produced counterexamples, namely examples of formulas, which, well, can be said to express consistency in a certain sense, but not in a literal sense, for which second incompleteness would fail. Okay, so that's the situation. Now, the good news from this study was the following, which is not very well known, I think, even among logicians, that even though we cannot define, or the science as of today doesn't know the answer to the question what it means that the formula faithfully expresses consistency. So we don't know. We can only judge by examples somehow. But nevertheless, Gödel's second incompleteness theorem, holds not only for formulas faithfully representing consistency, but for the much larger class of formulas, which can be mathematically well delineated. So, well delineated class of formulas supposedly containing all formulas naturally expressing consistency, but also containing many other formulas which may not actually express consistency naturally, but nevertheless, G2 still holds for them. Yeah. So put it more scientifically, so for those who did know this terminology, so essentially sigma 1 definable probability predicates in arithmetic defined by sigma 1 numerations in the sense of Pepperman. Yeah, so that's a sufficient condition for G2, even though, for example, Pepperman demonstrated there are many inequivalent over PA probability predicates satisfying this sigma 1 numerability condition. So in some sense, this means that fortunately G2 is a more general phenomenon, not restricted just to formulas intuitively expressing consistency or probability. Okay. Anyway, still this leaves more room for more investigation. So can I ask someone to run this? Oh, yeah. Sorry. So the next stage of our investigation of boundaries to this theorem is to actually somehow widen, to understand how wide is the class of theories to which Gödel theorem is applicable. And over the years, there have been attempts to improve G2 in the following respects. So first of all, we would like to weakening the axioms of piano arithmetic. So here we have some positive results and some negative results. The most, I think, advanced, or maybe not the most, but one of the most well-known advanced formulations of second incompleteness theorem is due to Pudlak, which essentially weakened the axioms of piano arithmetic down to Robinson's arithmetic Q, that is essentially PA without induction. The theory is very, very weak, not even able to prove the commutativity of addition. Still, under certain assumptions about Gödel numbering and about representation of probability predicates, Gödel second incompleteness theorem holds for theories extending Q. So that's a separate deep result involving substantial new ideas. However, it turns out that this example is not too far away from these non-Gödelian theories. And Dan Willard produced the first examples of theories weaker than Q. In the language of arithmetic, for which, however, that are able to express and prove their own consistency. And the key ingredient here was that the function s of x, mapping x to x plus 1, may not be total in this system. That's one feature that prominently appears in such counterexamples. However, Willard's examples suffered from another, let's say, drawback from the point of naturality. So they were just, let's say, well-defined theories. However, the axioms were not so meaningful mathematically. Maybe one of the crucial axioms that Dan Willard considered was, in order to violate Gödel's theorem, was to apply the fixed point. So one of the axioms was postulated as a fixed point of a formula expressing consistency. So something like the phi is equivalent to con t plus pi, where t is his theory. So in his setup for the fixed point theorem in arithmetic, Gödelian fixed point theorem did hold. So this was possible to do within this formal system T. And then the whole trick was to ensure that such a formula phi within the axiom, together with the axioms of T, can be actually consistent. T plus phi can be consistent if T is weak enough. So that's a phenomenon. And if it is consistent, then essentially from this equation, we will see that T plus phi proves con T plus phi, and that's a violation of Gödel's second. So that was Wheeler. There are many, one can produce many examples like this. However, the most, let's say, beautiful and meaningful example of this kind without the fixed point condition, but purely a theory given purely by a mathematical axioms is due to further Pascal, well known here again. And I will present it a few minutes later. So to say, at least I will formulate the system so that you can appreciate what kind of axioms one deals with here. Okay, so weakening axioms of PA goes up to this interesting theorem, which I think is a champion in counterexamples of that effect. But there are other phenomena or other conditions. The second condition that one can easily violate is condition that the set of axioms, or let's say the theory is recursively axiomatizable. In other words, is given by a computable or computably enumerable set of axioms. One can just say that, yeah, one of the basic conditions even for Gödel's first incompleteness theorem was that the set of axioms of the given theory is computably enumerable. Yeah, this condition is usually also inherited in the formulations of G2. One can weaken this condition and ask what will happen if T is not and here I think less well known but deserves to be better known counterexample is due to German philosopher Karl Nieberger. And I will start my presentation with this because it's a very simple, the simplest counterexample to Gödel's second incompleteness theorem if you want to have one. And the third direction will be the weakening the axioms of predicate logic. Gödel's second incompleteness, of course, is well known to hold for example, intuitionistic logic, which is already known classically. But nobody said that this is all that is possible in this regard. In fact, as it turns out, very little logic goes into the proof of G2. So it can be even stated for somewhat abstract formal systems having almost no logic. Abstract consequence relations having almost no logic in terms of not even implication is required to state G2. However, there are interesting formulations here, and counterexample that is from my joint work with Shamkanov. And that we presented for the volume, first strip volume dedicated to Albert Visser, where we presented certain anti-Gödelian phenomena for logic with fixed points and without contraction. So here the key ingredient is G2 requires contraction axioms. So that's one outcome of this study, which is good to know. And there are some counterexamples for systems without contraction which show anti-Galois phenomena. However, there are still some open questions here that I may formulate towards the end of my talk. Okay, so with this, I finished with this preamble. So my counterexamples I will be talking about is therefore these ones. So Nieberg examples. That's first, together with the work of my current master student, Lev Beklemishev, who studied this theory. Then I will present Pahomov's example, and if time permits, we'll say a few words about this weakening logic conditions. So that's the plan. So let's start with the Nieberg example. It's the simplest one, so I hope that it will be quickly understood. So that's nothing, let's say, nothing fishy about this. So let me stress that in all these examples, I'm talking about natural formalizations of consistency, not some trickery with how consistency is defined, right? So nothing fishy is going on about representation of probability predicate, consistency assertions, and these sort of phenomena. So these are natural as possible formalizations for which Gödel theorem is viable. It's not the theorem, but let's say conditions. Okay, so Nieberg arithmetic, as I said, it's about dropping the condition of your theories being RE. And even if you are asked, can you, let's think for a second for a simplest counterexample to G2. First thing that comes to mind, if you drop the condition of RE, let's take the true arithmetic. So all sentences of arithmetical language true in the standard model. Okay, so that's a theory, deductively closed. Doesn't prove its own consistency. So the problem is that the consistency of this system cannot be stated in the language of arithmetic. So this is not a counterexample. So how can we deal with this problem? So here is the answer. So consider two theories, T1 and T2. So T1 will be piano arithmetic plus all through pi1 sentences. Usually this set is denoted each pi1 of n. In other words, we consider, let's say, arithmetical sentences of the form for all x phi of x, where phi of x contains only bounded quantifiers. Only bounded quantifiers, and that's sufficient. Okay, so of course, this set of sentences is not RE. So the set of axioms of T1 is pi01 complete, and the set of theorems of T1 is sigma 2. So it's sigma 2 complete. However, we are not so worried about that it is sigma 2, but the good news is that it is sigma 2 defined. So there is, in fact, an arithmetical formula defining in a natural way probability in this system. It is constructed using the so-called definition of truth for pi1 sentences, which is well known to exist, and people deal with it all the time. So one can actually state the probability predicate for this system in a natural way. It will be a sigma 2 arithmetical formula. So that's T1. Now T2 is the theory which is PA plus this con of T2, consistency of T2. And by the way, for specialists, this consistency of T2 is the same thing as what we call sigma 1 reflection. But anyway, this is consistency of the theory T2. Now what we can observe is these two things. So firstly, T1 proves consistency of T1. T1 here, yeah. So now we observe that T1 proves consistency of T2. Why? T2 is an ordinary theory, a finite extension of piano arithmetic by a single axiom expressing consistency of T1. So it's an RE theory. It has a sigma 1 definable in a Pfeffermanian style probability predicate. That means a consistency assertion for T2. This is in fact a formula of the form pi1. So by the construction, con T2 is a pi1 formula. Probability in T2 is a sigma 1 formula, substantial formula. Now, is it true or is it false? Let's just ask ourselves this question.
If it is false, you're wrong.
No, I mean, the theory T1 is obviously sound, right? So it has only true axioms. So T1 cannot be inconsistent. It's consistent.
Yeah.
So if it is consistent, this formula is true, right? So, and if this formula is true, then the theory is sound. And that means that T2 is a sound theory. In particular, it is consistent. So con T2 is a true pi1 sentence. If it is a true pi1 sentence, it must be simply an axiom of T1. And so we have, now, on the other hand, we have T2 proves con T1 for obvious reasons, right? So it's postulated as an axiom. So we have already something strange. Two theories, one of them proves consistency of the other, and this one proves consistency of the other. So now Niebergard's arithmetic, called NA, is T1 intersection with T2. Now, what's intersection of two first-order theories? Well, that's a set of formulas that are provable in one of them and in the other. So the proof predicate for this system is just, let's say, let's denote it like it's box NA phi. It's simply, by definition, box T1 phi and box T2. So when we say that phi is provable in Niebergard arithmetic, we mean that it is provable both here and here. So this is all natural, no tricks. And then what we can conclude is if we substitute now bottom or falsity or 0 equals 1 for phi, we will obtain that box NA bottom is equivalent to box T1 bottom box 2 bottom, and negation of that consistency of NA. This is not box NA bottom. This is then essentially the same thing as con T1 or con T3. Your negation of this formula is a disjunction of two negations, which is respective consistency assertion. So you just obtain this obvious relationship. And so what do you see? That T2 proves Conti1. And then it proves Conti1 or Conti2. So in fact, it proves Con and A. And T2 proves Conti2, Conti2, and then it proves Con and A as well. Right? So conclusion is that Con and A is provable both in T1 and in T2. So T1 intersection T2 proves Con and A. So and A proves Con and A, and that's all there is to it. So to say, it's so I find it very nice. So as I said, I think this example deserves to be better known and go into undergraduate textbooks on Gödel theorem. But okay, now the more difficult question, and I think more interesting question, is that I asked my student Lev working, and namely, what is the probability logic of this strange arithmetical system NA? So probability logic is a model logic, so the logic formulated in terms of like propositional logic plus modality box, and box is interpreted as box NA in this case. So what kind of principles of probability in NA are true and what are false, and what principles of probability of NA are provable in NA itself. It turns out that the most well-behaved logic or the question to ask is what principles of probability in NA are verifiable in PA. So, from what we see here, it cannot be, the answer cannot be the standard answer Gödel logic. So it's not Gödel that we can be sure of, but the question is what fails and what new principles we have. It turns out that we have both failure of something and new principles of something. Now one can guess what is the failure. So we abstain, so we lose the condition of sigma 1 definability of probability predicates here. And the main consequence of these sigma 1 definability was the so-called third Loeb's condition or transitivity principle. That box phi implies box phi. So meaning that if phi is provable, then it is provable that phi is provable. So that is usually assumed in treatments of Gödel's second incompleteness. In fact, follows can be proven if box is sigma 1 and fails if it is, or can fail if it is not sigma 1. So in this case, this principle will fail. So we will be in the realm of non-transitive logics, in fact, so-called pre-transitive logics. So let me just show you what is the answer. So the logic of Niebergall arithmetic can be characterized by certain axioms as well as by a certain class of Kripke frames, which I will describe. Both are somewhat weird looking, so it's just probably interesting to have a look at the answer. And there is still some open question here, which we have not yet figured out, but so let us first indeed describe the class of, let's indicate our approach to this question and the answer. So it turns out that, well, this probability theories T1 and T2 can be expressed in terms of, let's say, theories which have already been studied from the point of view of probability logic, namely the theory T1. For example, if we denote it by box 1 probability in T1 and T2, and let's say by box 0 probability in PA, then in terms of box 1 and box 0, one can express our box NA. Now, how does it go? Well, the box NA and A5 is using this, of course, is the following. It means that box 1, 5 and box 0, not box 1, bottom implies 5. Because this is clearly the probability in T1, and this is the probability in PA together with the additional axiom expressing consistency of T1 using formalized deduction. So that's more or less how we can translate this T1 and T2 into box 1 and box 0. And the logic of box 1 and box 0, the probability logic of them is known, and it is presented in Bullo's book and has a name GLB, or bimodal probability logic. So it's a well-studied, although somewhat complicated system. So-called logic due to Japanism. Bimodal probability logic. Interestingly, the logic of box 1 here, which is also known RE, so it's T1. The logic of T1 is exactly the Gödel logic. The logic of box 0 is a Gödel logic, but these combinations, they already produce something more complicated. But at least we know how to axiomatize this logic GLB, and therefore by this interpretation we can infer, for example, from decidability of GLB that the probability logic of NA is decided. It does not yet tell us what class of Kripke frames it has, because unfortunately the logic GLB is not complete for Kripke frames. So we don't immediately obtain any class of Kripke frames. It requires some work, and we don't obtain any explicit axiomatization. Here is the answer that I would like to present. And by the way, when do I have to stop?
You have to leave this room at 2:30.
2:30. Okay. Oh.
We can go to another room.
No. I think that book is a good homework. Yeah. Takes more time than that's good. So okay, let's start with the Kripke frame. So as we know, the Kripke models for Gödel logic are finite irreflexive trees. So we have pictures like that. For example, something like that. And we interpret modality in such a model as being true in all worlds above. So these trees, transitive, irreflexive trees. Irreflexive trees. Now, what we have, what kind of models do we have here? So the answer looks somewhat strange. So let us define the thing I call needle tree. It's a technical term. So it's a tree which has needles, like a cactus. So namely, what are needles? Needles are little arrows that are protruding from every node of the tree. So they are not part of the stem, that's special kind of arrows. like that. There is at least one at every node. So, like,
The maximum height is 1.
yeah, they are just they're not trees growing at every node. They're just needles sticking out. So that's imagine such a structure. And now what you do? You postulate now your. So you postulate your binary relation as follows. So you still have a transitive irreflexive relation along the white lines of the tree. And moreover, if you have this needle, and then from the end of the needle, you must be able to see everything which is visible from the root of the needle. So there are arrows, implicit arrows, looking upwards at the white points from every end of every needle. However, the ends of needles do not see each other. So we don't have full transitivity here. So that's a partially transitive structure where we have transitivity along the white lines, and we have these additional strange arrows everywhere. But like here, for example, here, so that we implicitly have. But so these are the class of Kirchhoff frames for this probability logic of NA. That's theorem 1 by Lev Beklemishev. And let me give a couple of principles that are valid here, just to see that this is not completely an easy thing. So axiom 1. So box now means box NA, right? So that's this weird Niebuhr-Galt arithmetic. Box P plus P plus box. So this is a kind of weaker version of Lev. So if you just cross out box P here, you obtain just the ordinary Lev axiom. And here you have a strange disjunction, looking at the beginning. Axiom 2 is a kind of linearity, but it's even, you can say that this is a source of our main problems here, but yeah. That's another principle that is valid. And as a consequence of A1, from Lev, you can infer transitivity. From this weak Lev, you cannot infer transitivity, but you can infer a certain weaker form of transitivity, which is useful, which I put here. So box P implies box squared P or box P. So that's one shorter looking consequence of the principles that we have for this modality. Unfortunately, we don't have the result that this is a complete axiomatization of the logic, and we don't have a complete axiomatization in this language. However, what we can do is introduce into your language of probability logic a specific so-called propositional constant. Propositional constant is a special variable for which you don't consider substitutions. And the intuitive meaning of this constant, like, what do you call it, flat, or not flat, what do you call it, it's not a sharp, it's a more, so to say, well, anyway, denoted like this in the paper, or in P. So it is interpreted, in fact, as this formula not con ground. specific sentence will be denoted by this constant b. And then having this b in the language allows you to have a much nicer both logic and class of Pyrki model. So this b corresponds to these niggles somehow, and then you can formulate this kind of axiomatization, which is nicer looking. So let me do this as well. A1 prime. This one. Then we have it's in Sweden. B to box. No, B. So in terms of this new Niebergall arithmetic, this B behaves like a Gödelian fixed point. Strangely. And A2 prime, A2B is what remains of this ugly axiom A2, but now it's not so ugly. Okay? It's box B minus P or box P. Like that. And then, of course, you have necessitation, you have modus ponens, and that will be the full axiomatization of the logic of Niebergall arithmetic in this language extended by a propositional constant. So that's the best we were able to achieve. However, what's the axiomatization of the logic in the original language, just with one modality that we don't know.
Well, I couldn't follow this last part.
Beginning where?
Beginning that what is the positive result of your experiment?
Yeah, so consider the language of propositional logic extended by a propositional letter B. That plays the role of propositional constant. We forbid substitution rule applied to B, as you well know. Okay, now postulate these principles, in each of which B plays some role. This is like this is just a fixed point equation for B, uniquely defining this, in fact. And then this is a this disjunction type axiom, which is and then it turns out that a formula with or without B is provable in this logic from these axioms, even only if its translation is provable in PA. So that's the probability logic of Niebergall arithmetic in PA, or equivalently true in all such structures. Okay, so that's all I wanted to tell you about this Niebergall arithmetic. So let's go to other counterexamples. So I will quickly present this counterexample, for example, due to Pahomov, just to see yet another natural looking, in fact, I would say natural system for which G2 fails. So, and Pahomov example, he denoted his theory H less than omega. We'll see why. So this theory will be formulated not in the language of arithmetic, but rather in the language of set theory. So you have the signature. It's the ordinary first order theory in which you have equality, membership, and the special function he denoted V bar, which I would never denote it like this, but nevertheless, let's keep it this way. So, and the meaning of, let's say, the idea of the theory is that this theory postulates very weak principles of set theory. And the first two principles that we postulate, A1 is the principle of extensionality, according to one. And A2 is the principle of separation. So these are very standard fundamental axioms of it. This is of course A2 is of course a schema. So for every arithmetical formula phi with the free variable z and possible parameters, you have this. So, functionality separation. And the axiom A3 concerns this function V bar. And this is essentially defining axiom for V bar. And it is as follows. So we can say it like this. Y belongs to V bar of X if and only if there is a Z in X such that Y is a subset of V bar of Z. Now V bar intuitively, what is V bar? So we have, of course, a cumulative hierarchy, and so we have the ordinary universals. The alpha plus 1 is P alpha, and the lambda is the unit. Lambda is limit ordinal. So that's the standard from one hierarchy where we iterate the power sets. Now we can do that in the usual, let's say, Zermelo-Fraenkel set theory, because we have operation, the power set operation. So here we don't postulate the power set operation, but we sort of try to recapture something from there. And well, we can, having this hierarchy, we usually define the rank of a set as a minimal alpha such that X is contained in V alpha, right? So that's the rank in the von Neumann hierarchy. And so intuitively, V bar of X is simply the set V with the index row of X. Or you can say V bar of X is the first element of the cumulative hierarchy containing X. And that's essentially what is stated here. And notice that it does not refer to any power set, it just defines what it defines. So that's a very, very simple weak set theory, and to which we add finally, well, the property of this weak set theory is that it admits finite models. So if we consider Vn for a specific natural number n, so if we build up this hierarchy for finitely many steps, we are still in the finite universe of sets. And it will be a model on these axioms, no problem. So we are not guaranteed that next element of the universe exists because we don't have the power set operation. So this theory admits finite models. Now we want to prevent this because that's the key thing. And we add this axiom A4 or schema A4n, saying that roughly speaking, there is an x for every n. There is an x such that x is the n's ordinal. So put it in quotes. So this has to be appropriately formulated, but we can, let's say, denoting this formula as Cn of x, how we can define. So firstly, the nth ordinal is defined in the usual way. So 0. So we have empty set, empty. So these are phenomenal ordinals, usual way 0, 1, 2, etc. So these are the basic sets, the existence of which we postulate in this system. How can we state their existence? Well, we define sequence of formulas Cn of x by recursion, for example, like C0 of x, and will be followed x, so that defines empty set, that's Cn plus 1 of x. If you were in my theory class, I would ask the students to suggest an answer, but okay, I will just say there is a u in x, n of u, and for all x. Something like that. So maybe I made a mistake there, but one way or another you can formulate this condition. And so then this is in fact already the counterexample. Notice that there is no fixed point construction here. No axioms are formulated in terms of unnatural Gödel numberings or fixed point constructions. So then, of course, the situation needs to be analyzed, and there is a preprint by Feller that he has not published so far. There is a preprint, but there is no publication. So nevertheless, in that preprint, everything is more or less clear. So what happens is that, in fact, this theory turns out to be very weak in terms of proving the existence of facts, or let's say existence of facts above the given rank of sets. So it can, for every specific n, as we see here, it has a set of rank n. However, having that, it has various axioms that allow it, like separation, to define various things below it. But it cannot jump to the next rank because you don't have the power set. And this is similar to the phenomenon of Willard, where you don't have the successor function in your language. And here this plays also a role. And what also plays a role that these universes, these finite models, they have sufficiently many elements. They grow super exponentially, so to say. And what it turns out to be that with respect to probability of restricted pi1 sentences, and so pi1 sentences in relational language, this theory is almost, well, is as good as elementary arithmetic. So color exponential function arithmetic. So you can do quite a lot with probability of pi1, restricted pi1 sentences. But it is very weak with respect to higher levels of logical complexity. But pi1 is enough to express consistently. So that's how you, in fact, by analyzing this theory, can prove that it, in fact, is able to establish its own consistency. Again, if you have a finite, let's say if you have a finite subtheory of this theory, so you can also have the following intuition. So this theory is infinitely axiomized, and this is substantial. So if you restrict to finitely many axioms, you won't have finitely many instances of A4, so your ranks will be bounded by something finite, so we will have a finite model. So in some sense, you can prove consistency of this theory by producing finite models of finite parts of that theory. And that's, in fact, turns out to be formalizable in the theory itself. So that's more or less how it is working. Okay. Okay, so that's Pahomov. Yeah. I think I will stop here. So about the logic, I can only refer to that paper we had with Daniel about in the volume dedicated to Albert Visser, where we have certain effects, anti-Gödelian effects for logics without construction. Thank you very much.
Yeah, thank you very much. I will now stop the recording.